Hello. So, in this lecture we are going to talk about turbulent boundary layers. Now, in this module we have been talking about turbulent flows, whereas we looked at boundary layers and in particular laminar boundary layer in the previous module. So, when we talk about turbulent flows in the previous two lectures, first we talked about what are the characteristics, properties of turbulent flows, and then we said that it is characterized by the randomness, and therefore, the velocities will have a lot of fluctuations. So, to define turbulence flow or to analyze turbulent flow, we can decompose into the mean velocity and fluctuating velocity, and then we showed the equations for mean flow. We did not derive it, but we said that if we average the Navier-Stokes equations over a sufficient length of time, then we will get what is called Reynolds average Navier-Stokes equations for mean flow, and it will have an additional term when you compare with the Navier-Stokes equation, and this term was of the form rho u dash over bar, where bar represents the averaging. Now, this rho u dash or rho u dash v dash, this is Reynolds stress or the stress caused by turbulent fluctuations or a form of stress. So, that, and then in the next lecture we talked about flow in a pipe, and we saw that based on the experimental observations one could develop an empirical relationship of the form of power law, where u bar is equal to u into 1 minus r by capital R raised to the power 1 by 7 or raised to the power 1 by n. Such kind of power law was developed for velocity profile in turbulent pipe flow. Now, we could see that this power law profile was not valid in the near wall region. So, that is why in the near wall region people studied the velocity profile carefully, and it was observed that for all the cases, it may be a turbulent flow in a pipe or a turbulent boundary layer, there was a universal behavior in the near wall region, and one could define a viscous sublayer where viscous effects are important, and then a outer turbulent layer where the turbulent effects are important. So, now with all this background, we will try to understand a bit more about the turbulent boundary layers and try to use momentum integral equation. So, remember when we talked about laminar boundary layers using Reynolds transport theorem, we derived a momentum integral equation which could be used to analyze the integral quantities for a boundary layer. So, let us look at this first. So, this is a typical image for a boundary layer over a flat plate that we have been discussing. So, this is the laminar boundary layer, and here you have a turbulent boundary layer. Of course, you can see that the turbulent boundary layer is significantly thicker than what you have say for laminar boundary layer. So, turbulent boundary layer is thicker. The slope you can see here, the slope is smaller, and slope in the turbulent flow is significantly larger. So, as you move along the plate with x, the growth of turbulent boundary layer is faster with x. So, as we move along the flat plate. Now, in unlike say in pipe flow, when we talk about, we say that when you increase the velocity, if you are talking about same fluid, if you increase the velocity or if you increase the flow rate, then the flow becomes turbulent. Whereas, in a when you are talking about flow over a flat plate, then what happens that initially up to a certain distance from the leading edge, let us say this distance is, you call it x critical, the the boundary layer is laminar, and then after that it starts becoming, or it transitions to turbulent. So, it will depend, for example, for if your plate is long enough, then for every flow velocity you might have a turbulent boundary layer over a flat plate. Now, so next question comes, when do we say, or what is the this number for x critical? Now, it will depend on a number of factors. The first and foremost is, of course, the plate should be smooth. So, all the analysis that we have been talking about, everything, we have an inherent assumption that the pipe is smooth or the flat plate is smooth. If you have a roughness on the plate, then that may trigger turbulence earlier. So, it will depend on the roughness, and it will also depend the other disturbances that may cause lot of disturbances to the flow, and the turbulence may trigger at an earlier length. In general, the number that is accepted or quite often quoted is Reynolds number, say Rex of 5 into 10 raised to the power 5 is considered to be the critical Reynolds number based on x. So, this Rex is basically u infinity x divided by nu, where nu is the kinematic viscosity. So, that is the number generally used. Now, if your flow is relatively free from disturbances, then this number could be, say, 3 into 10 raised to the power 6, or if there are a lot of disturbances, then this number could be 1 into 10 raised to the power 5 or so. So, this is just a number that you could use for analysis. Okay. So, that is the number, and from this you could calculate what is the value of x for a given value of u infinity, what is the value of x at which the flow of a particular fluid. So, fluid will come, or property of fluid will come in nu. So, for a particular flow at a particular fluid velocity u infinity, what is the number when the or what is the length at which the boundary layer will become turbulent or will not remain laminar anymore. Now, unlike laminar boundary layers, in the laminar boundary layer we said that in the boundary layer viscous effects are important, whereas in the turbulent boundary layer we will have layered structure. So, remember when we talked about near wall turbulence in pipe flow, we said there are 3 layers, the viscous sublayer and the outer layer, and in between the buffer layer or what is called overlap layer. So, similarly we have 3 layers, or you can say 2 layers in turbulent boundary layers. It is same in both the cases. The only thing is that we say that in the viscous sublayer the viscous effects are important, and in the outer layer the viscous effects are not important, or the turbulent effects turbulence effects are important. Now, because we need to have an overlap region, so there is a buffer layer or the overlap layer, what we call so we call it 3 layer structure. So, there is no inconsistency, so to say. You could even say that this is a 3 layered structure. So, but from the physical point of view, there is a very thin layer near the wall in which viscous effects are important, which we call viscous sublayer, and the outer layer where turbulent fluctuating motion is important and it causes the friction, and where the Reynolds stress will be dominant. So, this is fully turbulent, what is called outer layer. Remember that this is not the this is not this outer flow, whereas this, when we talk about, we have a viscous sublayer and a outer layer, and in order to match these two we will have a buffer, or to have same nomenclature we should call it overlap layer. So, that tells us that the logarithmic law, the linear velocity profile in the viscous sublayer u plus is equal to y plus, and logarithmic law that u plus is equal to some constant into L and y plus another constant, that logarithmic law was valid in the overlap layer. So, we could still have those laws valid for the turbulent boundary layers, and we will use them. Okay. So, let us look at the turbulent boundary layer on a flat plate, and we will consider that this plate is smooth, there is no pressure gradient along the flow direction. So, first we will write down the momentum integral equation. So, this momentum integral equation we derived when we looked at the boundary layers. So, in this, if we say that the pressure gradient is 0. So, from because in the boundary layers when the pressure gradient is 0. So, that means dP by dx is equal to 0, and in a boundary layer, when we derived boundary layer equation, we said that dP by dy is approximately 0. So, pressure is not a function of y. So, the same pressure field what is there in this outer flow will be valid in the boundary layer. So, we could write that P plus half rho u square in the inviscid region, and from that if dP by dx is equal to 0, we can deduce that du infinity by dx is also going to be 0. So, this term will go away. Now, just to remind ourselves, we looked at the governing equations for laminar boundary layers, where we took the two dimensional equations in Cartesian coordinate for flow over a flat plate. So, the similar equations one can write down for turbulent flow over a flat plate. The only difference will have that we will have an additional term in terms of Reynolds stress, and these equations will be for the mean flow or mean velocity and mean pressure field. Okay. So, this equation simplifies to tau w by rho is equal to u infinity squared d theta by dx. Now, we will also bring into picture the definition of Cf, which we called skin friction coefficient. So, it is nothing but a non-dimensional form of wall shear stress. So, you have tau w and it is being non-dimensionalized by half rho u infinity square, where u infinity is the free stream velocity. Now, if we look at these two equations, then we can write that tau w by rho is equal to Cf by 2 into u infinity squared, and we can substitute this here. U infinity squared will cancel out, and we will get what we will get is Cf by 2 is equal to d theta by dx. Remember that this theta is momentum thickness. So, this form of momentum integral equation is valid for laminar as well as turbulent flow. The only assumption here we had is that the pressure gradient is 0. Now, we also bring into picture the definition of friction velocity u tau, which we defined to define the velocity profile near the wall. So, u tau is called friction velocity. In many places you might also see it as written as u star. So, this is equal to tau w by rho raised to the power half, and this will give you a unit of velocity. So, we can write from tau w by rho, we can use C f by 2 u infinity squared. So, u tau will become u infinity C f by 2 raised to the power 1. Again this has an assumption that dp by dx is equal to 0. So, we cannot use it always, only when dp by dx is equal to 0, then we can use u tau is equal to u infinity square root of C f by 2. Okay. Now, the question comes that what we need to do is solve this momentum integral equation, and we solve the momentum integral equation for laminar flow over a flat plate where the pressure gradient was 0. Now, in this case when we talked about laminar flow over a flat plate, we assumed a velocity profile, and that velocity profile was parabolic velocity profile, probably in analogy with what we observed in flow in a say laminar fully developed flow in a pipe. So, if we what we could do, we could assume a power law kind of velocity profile, or say 1/7th power law kind of velocity profile. But the problem with this profile is that it is an approximate profile and it is not valid in the near wall region. We saw in the previous class that if you use power law velocity profile in the near wall region, that then you will get the gradient of this mean velocity to be 0 at the wall, and that will result tau w being 0, which is not true. So, we could not use, because in that case our CF or tau w useful results. So, what we could do, the another velocity profile we have, especially in the near wall region, is logarithmic velocity profile, which is for the overlap layer region. Now, overlap layer region means it matches down to the viscous sublayer and it matches to the outer layer. So, so we could approximate that the logarithmic, or we can assume that the logarithmic velocity profile is valid across the turbulent boundary layer, and using that we could derive the or we can analyze the momentum integral equation. So, we will do that. This is the logarithmic velocity profile, which is basically u bar by u tau, which we call u plus also, is equal to 2.5 times ln y u tau by mu by nu plus 5. So, this is also called y plus y u tau by nu. Now, we can when y is equal to delta. So, that means at where delta is the disturbance thickness or boundary layer thickness. So, at this region, at this point, if the free stream velocity is u infinity, then u bar will be equal to u infinity. So, we can write this equation, we can substitute u bar or mean velocity is equal to u infinity and y is equal to delta. Okay. Now, in the previous slide, we looked at CF by 2, we could write that CF by 2 square root is equal to u tau by u infinity. Okay. So, we could substitute this value here, that will be square root of 2 by C f. Similarly, we could rearrange this. So, we can write this delta u infinity by nu into u tau by u infinity. So, this is a kind of Reynolds number where the length scale is delta boundary layer thickness. So, we will call it as R E delta, which represents that the length scale here is delta boundary layer thickness. So, then we can substitute u infinity by u tau is equal to square root of 2 by C f is equal to 2.5 ln R E delta, which is this, and u tau by u infinity again square root of 2 by C f plus 5. Now, we have brought in the form of C f, this equation has come in the form of C f and delta, which is basically hidden in this R E delta, as you can see from here. Now, what we do is we could write, using this equation, we could find out the value of C f for different R E delta. You will need to do a bit of iteration, but that is very simple. You could code this in an Excel and try to find out the values. So, what I have done, I have calculated it for different R E delta, the values of C f, and as suggested say by F. M. White, that we could fit in this data and try to find out a equation. So, that equation, if you find the best fit curve for this data for using these 4 data points only, then you will get a simpler relationship, because this relationship, though it is accurate one or relatively accurate, but it has logarithmic form. So, to simplify the mathematics, what they suggested, that we could write down a simpler relationship between C f and delta, and which will be valid for at least these value of R E delta. Remember that this is R E delta, not R E x, and delta is less than x. So, that is why this 1 raised to the power 1 into 10 raised to the power 4 and 10 raised to the 5 are coming into picture here. Okay. Even in these values of Reynolds number delta, R E delta, the flow will be turbulent, because R E x will be much higher. So, we will have C f when we fit into this, we can write this 0.02 R E delta raised to the power minus 0.165, or which is close to R E delta raised, or this number is minus 0.166. So, we can write in this form 0.02 R E delta raised to the power minus 1 by 6. Now, what we have is a simpler relationship between C f and delta. So, our momentum integral equation, when we wrote down it in terms of C f, it was C f by 2 d theta by dx. Now, theta, remember that it was that we will need to know the velocity profile, integral 0 to delta u by u infinity minus into 1 minus u by u infinity into dy. So, we will need to know u as a function of y, or u by infinity as a function of y by delta. So, we need to know the velocity profile, and we could use, because in the entire boundary layer we have assumed the logarithmic velocity profile. So, we could integrate that velocity profile, but again the integration will be quite involved. So, what one could do is, one could use the power law velocity profile to find out theta. Okay. So, if we do that, we already have C f in terms of delta, and if we calculate the theta in terms of delta, then we will have a differential equation for delta. We can solve this differential equation with certain limits, and then we will be able to find what is the expression for delta. So, to calculate momentum thickness, we can assume empirical velocity profile, which is 1/7 power law velocity profile. Now, for a pipe flow, we had 1/7 power law velocity profile was u bar by u is equal to 1 minus small r, where r is the radial coordinate, small r, divided by capital R, which is pipe radius raised to the power 1 by 7. Now, in analogy with that, we could write for turbulent boundary layer u bar by u. This basically is, you could write it r minus r. And what is r minus r for a pipe flow? So, this is small r, this is capital R, and basically this value is capital R minus small r, which is the distance from the wall. So, we can write if this is y, so distance from the wall y, and in place of r we will use the turbulent boundary layer thickness. So, y by delta raised to the power 1 by 7. So, that is what we will have, that in the turbulent boundary layer u bar by u, it actually should have been u bar by u infinity is equal to y by delta raised to the power 1 by 7, because we are using u infinity as the free stream velocity. Of course, again it will not be valid close to the wall. That is the reason that we have used the logarithmic velocity profile to calculate wall shear stress. Okay. So, let us calculate momentum thickness theta by substituting the velocity profile. Now, we could simply solve this integral by assuming, say, that y by delta raised to the power 1 by 7 is equal to eta. So, that will give us that y by delta is equal to eta raised to the power 7. Or from that we can write that dy is equal to 7 into delta into eta raised to the power 6 into d eta. So, we can substitute this for dy, and the limits will be that when y is equal to 0, eta will also be 0, when y is equal to delta, then eta will become 1. So, we will have our theta is equal to integral 0 to 1, the limits, and the first term y by delta raised to the power 1 by 7 will become eta. The next term within the bracket will be 1 minus eta into 7 delta eta raised to the power 6 d eta. Now, delta is the boundary layer thickness. So, it is constant with respect to y, 7 is a constant. So, we can bring them out, and that will basically become, when you bring all those terms together, that within bracket you can have eta raised to the power 7 minus eta raised to the power 8 d eta. And when you integrate it, this will become eta raised to the power 8 divided by 8 minus eta raised to the power 9 divided by 9, and after substituting the limit, you will have 1 by 8 minus 1 by 9. So, that will be 9 minus 8 by 72 or 1 by 72. So, you will have theta is equal to 7 delta by 72. So, now we have CF in terms of delta, we have theta in terms of delta, we can substitute both. So, when we substitute in this, then this delta CF by 2 will become simply 0.01 RE delta raised to the power minus 1 by 6, or we can write RE delta in the expanded form, where we have delta explicitly, u infinity and nu are constant. This is equal to 7 by 72 d theta by dx. So, this will be d delta by dx. Now, we can integrate it, we can take the variables on each side. So, we can take delta on one side. So, that will be delta into 1 raised to delta raised to the power 1 by 6 into d delta is equal to 72 by 7. So, that will come here 72 by 7 into 0.01, which will give us 0.1033 and u infinity by nu. So, and this is multiplied by dx. So, dx into u infinity by nu raised to the power minus 1 by 6, and when you integrate it, that will be delta 1 by 6 plus 1. So, 7 by 6 delta raised to the power 7 by 6 divided by 7 by 6. So, it will become 6 by 7 delta 7 by 6, and all this is constant. So, we will have simply x here plus a constant of integration. Now, the next question comes, how do we find this constant? So, a gross assumption probably has been made, but that is neglecting the laminar boundary layer over a leading edge. So, the assumption is that when you talk about turbulent boundary layer, there is in the certain region there is laminar flat plate. So, it does not start at x is equal to 0, but what we assume here that this turbulent boundary layer starts from x is equal to 0 itself. So, that is the assumption that at delta at x is equal to 0, delta is equal to 0. So, that will be 6 by 7 delta raised to the power 7 by 6. So, this constant basically becomes 0. Now, we can rearrange it in a simpler form. So, we can do this and we will get delta is equal to Re x raised to the power minus 1 by 7 into x multiplied by some constant. So, that will give us delta by x is equal to 0.16 Re x raised to the power minus 1 by 7. So, we get a relationship for turbulent boundary layer thickness. The assumptions here at the plate is smooth, the pressure gradient over the plate is 0. The other assumption we have assumed the velocity profiles. We have assumed, remember we have assumed two velocity profiles. We have assumed the power law profile to calculate momentum thickness. We have assumed the logarithmic velocity profile to assume tau w. Now, if the integration is cumbersome, probably we could use the logarithmic velocity profile for both the cases and use the numerical integration to simplify things. So, this gives us a relationship for turbulent boundary layer thickness. Now, we could use this expression to calculate Cf or skin friction coefficient. So, that is 0.02 Re delta raised to the power minus 1 by 6, and we can substitute the value of delta here, and what we will get after a bit of algebra, we will get Cf is equal to 0.027 Re x raised to the power minus 1 by 7. So, that is skin friction coefficient. Okay. Now, we know the skin friction coefficient, we know the boundary layer thickness. We could also calculate what is the drag on a flat plate, let us say where the turbulent boundary layer starts from x is equal to 0 itself. So, that will be tau w into b dx, where b is the plate width normal to the screen. So, we can write tau w in terms of C f into half rho u infinity squared into b dx, and then we can replace the value of C f there. So, C f is basically 0.027 into Re x raised to the power minus 1 by 7, and half rho u infinity square is constant with respect to x. So, that can come out of the integral, and b and 0.027 are also constants. So, we basically have a constant into integral 0 to L x raised to the power minus 1 by 7 dx, and when we do that and put the limits, then what we will get from this integral x raised to the power minus 1 by 7 plus 1. So, that will be basically 6 by 7. So, after substituting the limits, you will get 7 by 6 into L raised to the power 6 by 7. So, that is your drag force. Now, we can simplify this further and write this down in terms of drag coefficient. So, drag coefficient is drag force divided by half rho u infinity squared multiplied by weighted area. Remember that for a flat plate which is aligned with the flow, we use the weighted area, and in this case we assume that flow is happening only on one side of the plate. If the flow is happening over both sides of the plate, then this will be 2 BL, but here we assume that this only on one side of the plate. So, area is BL, and we can substitute the value of FD from here. The rho infinity squared will cancel out, B will cancel out, and what you will get is this 0.027 u infinity by nu whole raised to the power minus 1 by 7 into 7 by 6 L raised to the power 1 minus 1 by 7. So, when you combine this and this, you will get REL raised to the power minus 1 by 7 multiplied by 7 by 6 into 0.027. So, that will give you the drag coefficient. CD is equal to 0.031 or REL raised to the power minus 1 by 7. So, all that analysis has given us that how we can calculate the drag force in a turbulent boundary layer with an assumption that the turbulent boundary layer starts from the leading edge of the plate in the calculation of delta as well as in the calculation of CF. So, it has been suggested that if we one need to take into account that the boundary layer is laminar near the leading edge and the transitions to turbulence at some distance, the drag coefficient, an adjustment can be made in the drag coefficient, and this formula has been given. Now, this is CD is equal to 0.031 divided by REL raised to the power 1 by 7. So, the same formula which we just derived for the turbulent flow over a flat plate minus 1 by 1440 divided by REL, and here the assumption is that the transition starts at Reynolds number, say this is REX at 5 into 10 raised to the power 5. Now, this 1440 by REL comes into actually it should have been divided by REL. So, this is basically this number 1440 comes from that RE transition into CD for turbulent flow minus CD for laminar flow at the transition Reynolds number. So, we can actually calculate that we can substitute these values that RE transition is 5 into 10 raised to the power 5. The number comes out to be 1438, and so it has been approximated to 1440. So, we could use that to take into account that in the initial length the flat plate has laminar boundary layer and then it has turbulent boundary layer, and the drag coefficient can be calculated using this. Okay. So, what we have done today is we looked at turbulent boundary layer. We discussed that in the turbulent boundary layer it grows faster, it is thicker, then you have a different region viscous sublayer and the outer layer. The universal log law of the wall that we talked about in the pi flow is also valid for the turbulent boundary layers, and then we use the momentum integral equation to analyze the integral quantities for a turbulent boundary layer over a flat plate with 0 pressure gradient. In doing that, what we did is because we needed wall shear stress in terms of delta or CF in terms of delta, and we needed momentum thickness in terms of delta. So, we assumed a logarithmic velocity profile, which is basically u plus is equal to 5 times ln y plus 5 for which is valid near wall region. So, we use that velocity profile, calculated wall shear stress, and then momentum thickness, we for that we used power law velocity profile, and then we also assumed that the turbulent boundary layer starts from the leading edge, and using all those assumptions we derived the expressions for turbulent boundary layer thickness and CF, or the skin friction coefficient. Now, you might see in the books, or there is another analysis where one could use the value of tau w in analogy with the pipe flow, and from the which is in terms of the distance from the wall and so on. So, one could use that expression, and one will end up with slightly different equations for delta by x and CF. So, it is not important to remember these relationships, but it is important to see that how does this vary, and the turbulent boundary layer varies faster than the laminar boundary layer, and how do we do this analysis, the assumptions that we have made, the velocity profiles that we have assumed. So, consider this as a kind of a problem, that if you have a velocity profile given, how you can use the momentum integral equation to find out the integral quantities. Okay. So, we will stop here. Thank you.